Okay, good morning again, everyone. And before we proceed, any questions from Monday's lecture? No? Okay. If no questions, then let me get back to the problem which I was not able to answer. So let's revisit it. So remember what we were talking about. We were talking about, first we talk about CPU scheduling. Then we said, okay, if we can schedule multiple processes, then maybe they need the same critical section. And we don't want them to enter the same critical section at the same time. So for that, we need to do the synchronization. And for that, we talked about first about Peterson algorithm. Then we saw what is the problem with Peterson algorithm. Then we talked about other solutions like atomic operations, for example, test and set or compare and swap, and how we can use the barriers to tell the compiler not to reorder the instructions, right? But when we are looking at the solutions to achieve mutual exclusion or to solve the critical section problem using test and setter and compare and swap, so we said that yes, we can achieve the mutual exclusion, we can achieve no deadlock guarantee, but we cannot achieve the no starvation guarantee. So, let's revisit our solution using test and set, and then we come back to the problem that how we can improve this solution to guarantee that there is no starvation. So let's have a look again. So I'm not going to talk again about how test and set works because we have covered it in the previous lecture, right? So if you look at this solution, so let's say you have the same code for two processes or two threads, doesn't matter. But what is important here is that this while statement, which is actually executing test and set on a lock variable, which is a global variable shared among two processes. Since test and set is atomic instructions, so what it will do is that it will set the value of the lock equal to true and return the old value. So if the old value was false, it's mean I have set it to the true. So which means that I get the lock. Right? But if the old value was already true and I'm again setting it to true, it's mean already someone has set the value of lock to true, and that person or that process who set the value of lock equal to true has the lock, and I don't have the access. So if this test and set return me the value of true, the old value of true, I will keep spinning in the while loop. But if the old value returned by test and set was false, the loop will break and I will be able to enter the critical section, right? Everyone is with me on this, right? Okay, so we said that this solution doesn't guarantee that there is no starvation. Why? Because it is possible that there is a situation where each here you can see that before after leaving the critical section, the process sets the lock equal to false. A situation can arise where the same process can repeatedly successfully get the lock. So it gets the lock, then releases the lock, again gets the lock, again releases the lock. And as a result, the other processes can starve, which means that they will never able to get the lock. So how we can solve this issue? So I'm skipping these comments because these are the same thing which I have said. So by rewriting our program and introducing a new algorithm where basically what we are trying to achieve is we ensure that if, let's say, there are 4 processes which are sharing the lock to enter the critical section, then they always take the turn. It never happens that the same process keeps getting the lock again and again. So if process 0 gets the lock, then after that, the next process which will get the lock will not be process 0 if there are other candidate processes there if they are waiting, right? So how this happens? So let's say we have 4 processes, P0, P1, P2, and P3, right? And they have some global variables, which are, one is the array, waiting array. It has 4 elements, same number of elements as number of processes, 0, 1, 2, 3. And it has also, they also share a global variable key and another global variable lock, which is initialized to 0, right? And all of them have the same code, right? So their remainder section can differ, but otherwise, the entry section and the exit section is the same, right? So let's say that all of them first execute their first statement, which is waiting I is equal to true. So each of them set their array elements equal to true. And then each of them write the queue, doesn't matter who is the final writer, the final value of the key will be equal to 1, right? Okay, then let's say all of them are running, let's say we have 4 cores. All of them are running at the 4 different cores at the same time. So all of them execute this while statement. So waiting I is true for each one of them, key is equal to 1, so while condition is true. So they enter into the body of the while and they do the compare and swap instruction. Now remember we said that compare and swap instruction in a multi-core platform can be executed only by one thread or by one core at a time, which basically means that other cores or other threads will have to wait. So let's say we assume that P1 is the key and it gets the chance to execute the compare and swap. So now it executes the compare and swap. It says, okay, is the expected value equal to 0? Yes, expected value is equal to 0. So what it will do, it will set the value of the lock equal to 1 and return the old value, right? So the old value of the key is equal to, old value of the lock is equal to 0, which will be set equal to key. So where you get, here you get 0, right? And then it sets its own waiting I is equal to false, which is, no, not this one, sorry, this one, right? Now, let's see what happens. Now, let's say when P1 is done with compare and swap, then we said, now let's say P2 tries to execute the compare and swap because P2 fails. So if P2 fails, so as we said, only one of them can execute. So let's say after P1, the compare and swap by the P2 is executed. If the compare and swap by P2 is executed, what it will do, it will check, is the expected value of lock equal to 0? No, it is not, right? So the value will not be overwritten, but the old value will be returned. But now the old value is 1, right? So if the old value is 1, so key will be set equal to 1. And it will go back in the while condition. So while condition waiting I is equal to true. I here is P2, right? I'm talking about now this one. So I is equal to key is equal to 1, so it will keep rotating in the while loop, right? So this one will keep rotating in the while loop, but this was able to, it checked the while loop and then it entered into the critical section. But before entering the critical section, it set its while waiting equal to false, right? So it entered into the critical section, and same will happen for all other processes. You can do it for yourself. You can see like P2, P3, and P0, they will keep rotating in the while loop. Why? Because for all of them, waiting I is equal to true and key is equal to 1. And they cannot do the compare and swap because the expected value of lock is not 0, it is 1, right? So key will never become 0 and they will keep rotating in this while loop. All of them will be rotating in the while loop. Only P1 will be able to continue. So here we are achieving the mutual exclusion, but we are trying to focus on how the no starvation is guaranteed. We will see how. Okay, so after entering into the critical section, what does P1 do is that it sets j is equal to I plus 1. So here I is equal to 1. So j is equal to I plus 1 remainder n. So I plus 1 is 2. 2 remainder n is equal to 4 because we have 4 processes. So you get 2, right? 2 remainder 4 is 2, right? And then while j is not equal to 1, not equal to I, yes, this condition is true. And weighting of j2 is not, what is weighting of j? This one. So weighting of j is true, and then you take the reverse, so it becomes false. So the whole condition of the while statement is false, so you don't enter the body of the while loop, right? This while statement. And then you come to the if else statement. If j is equal to I, no, j is 2, I is equal to 1, so skip it. So what you're doing is weighting of j is equal to false. So this one is that. So basically what this code is doing, this part of code is doing is this. It keeps looking, said, okay, I am the process P1, but I will look if there is any other process other than me who is waiting to enter the critical section. If it is, I will give it the chance. So how I'm giving it the chance? By setting its waiting entry equal to false. If I set, for example, here I'm setting the waiting entry of P2 equal to false. So if I set its waiting entry equal to false, then if you look at the top while statement, now if waiting j is equal to waiting 2 is equal to false, the loop will break and I will be able to enter the critical section, right? So if now let's not go to the P2, let's continue. Let's assume that we still focus on P1. So because we are saying that everyone will get the turn to enter the critical section. So if P1 has already once entered the critical section, it should not be allowed to enter again. Let's say if this is achieved or not. So after setting j equal to 2 and setting weighting of j equal to false, the execution of P1 goes back to the start of the value, right? So it sets itself weighting I equal to true, right? Actually, sorry. Yeah. And then t is equal to set equal to 1. I'm not writing because it's already 1. And then weighting of 1 is true and t is equal to 1. And then the process P1 again tries to execute compare and swap. Let's say it gets the chance. Let's assume it gets the chance. It gets the chance and it says if the old value, expected value of the lock is equal to 0. No, it is not. Right? So it compare and swap returns the old value of t, which is 1. So this process now actually starts, it gets stuck in the loop, right? Confused? If you're confused and you don't understand, tell me. Otherwise, yeah, go ahead.
I'm confused, but I'm not really sure.
So where, yeah, what part you don't understand?
If it goes back to waiting,
if P1 goes back to waiting, yeah.
Then these processes just continue the cycle, waiting over and over and over again. How does it end?
Okay, so look at the P1. So let's start again from the remainder section, from the end of the value, from the perspective of P1, right? So it goes back to the top of the body of the while loop. It sets its weighting I equal to true. So we set weighting of 1 equal to t true. T is already 1, so I didn't override it. So now you do the first while statement in the body. So weighting of 1 is true and t is equal to 1. So I can enter the body of this internal while and I can execute compare and swap, right? So now I look at compare and swap, and what I'm saying is if the expected value of lock is equal to 0, then set it equal to 1. But what is the value of lock? On the board, you can see it is 1, right? So the lock will not be overridden. And the other feature of compare and swap is that it returns you the old value. So old value is 1, right? You can see on the board. So it is set equal to 1. So now what happens is that this process P1 will again go to the while, internal while, right? Again, the condition will be true. Again, it will do compare and swap. Let's say it gets the chance to compare, but it is never able to break the loop, right?
Yeah, so it just stays in that.
Yeah, it just stays there. But however, it was once able to enter the critical section.
Yeah.
Yeah. So
every time they go into the internal while loop, they're setting lock to 1, no matter what is happening, no matter what the value.
At the start of the world, the first one who was able to do the compare and swap set the lock from 0 to the 1. But after that, no one is able to do that. Okay. So if no one is able to do that after that, then how they enter the other ones, how they enter the critical section, right? Right?
Okay.
So let's have a look. Have a look. Now let's say that P2 gets the chance. If you want, I can also do P3, but you can do P3 on as a practice at home, but I'm continuing with P2. Let's say that, okay, so now P1 is stuck, right? And remember, we assume that these 4 processes are running on 4 different cores independently. So let's say that P2 has P2 was stuck at the while loop, right? Why it was stuck? Because weighting of I, basically weighting of 2 was equal to true and key is also equal to 1. But however, when this process sets weighting of j equal to false, here, so then this first while loop breaks from the perspective of process 2. If its first while loop breaks, it even don't execute compare and swap, right? Its control will fall through, and what it will do is that it will set weighting I equal to false again, which was already false, so I'm not overwriting. It was set equal to false by process P1, right? So then it enters the critical section. So initially it was iterating here in the while loop, but then it enters the critical section here. And then what does it do? Here I is equal to 2, so j is set equal to I plus 1, 3, 3 remainder 4, 3. And then is j, while j is not equal to I, yeah, that is true. I is 2, j is 3. And weighting of j is, and j is not weighting. So basically we are saying that the process 3 is false, but it is not false. So, I mean, if you take the negation, so the whole condition will become false, and as a result, you will not enter the body of this second while, and you will come to the if else statement. J is not equal to I, so we are not going there, and we are setting weighting of j equal to false. So here, what you are basically doing is you are setting this equal to false.
When would we enter that second inner while loop?
Which one?
The j not equal to I.
This one?
Yeah, when would we enter that?
Okay. Anyone who want to answer this? When will we enter this one? This body of this while loop? Yeah.
That's like if you're checking from 1, if 2 is free, but it's not, so you go to the next one, which is 3.
Yeah, so the purpose of this while loop is keep checking if there is a process which is not waiting. If there is a process which is not waiting for the to enter the critical section, then you will skip that process and move to the next one. So that's why you are incrementing it once more. Let's say that our process P2 was not waiting, right? So F was false. So this body you will enter the body. So you will increment the J and you will then move to the next process 3. Okay. So anyway, here we are setting J equal to 3, and then we are setting it equal to false, right? And let's say I'm not going to the process 3 for the time being. I continue here. So after this, I go back to the start of the body, and from the perspective of process 2. I'm going back to the body of the while loop, and then what I'm doing is I'm setting weighting I is equal to true. So this is true, right? Key is already 1, so I'm not updating. Then I can enter the body, weighting I is true, key is equal to 1, but when I do compare and swap, I get back what? Key equal to 1. So I keep rotating. So this gets stuck in the critical, in the while loop. But it once entered the critical section. Now, if you look at the P0 will not, let's say I don't execute this one for the time being. Let's say I look at P0. So if you look at the P0 was stuck at the while loop. So here what is happening? Weighting I is equal to true, yes. And T is equal to 1, yes. It also does compare and swap, and it gets the value of P equal to 1 again, because code value of lock is equal to 1, right? So it never gets the chance to enter. Who will get the chance? Only P3 will get the chance. And you can, do you want me to iterate, do the same thing for P3, or everyone gets the idea? So P3 will also actually do the same thing. It will enter the critical section. It will set J equal to 0, and then it will set this one equal to false. And then when it will go back, it will get stuck. Okay, and then after that, P0 will be able to enter the critical section. And then it will set J equal to 1, and so on. You will continue. So they will keep taking turns. P0, 1, 2. So we started from P1, P1, P2, P3, P0, P1, P2, P3. Okay. Any questions? But I will strongly recommend you to do the same thing what I did on the board on your notebook, so that you internalize, you are able to absorb it or completely understand. Because I still, from your face expressions, I can still see there are some confusions, but they will go away when you will do it on your notebooks. Okay. Any questions? No? Okay. So before going to semaphores, or semaphores, I don't know what is the correct pronunciation, but so remember, when I started, like in one of the first lectures, I said that we don't need to memorize the information. Okay, what is a log, what is a mutex, what is a critical section, what is semaphore, blah, blah, blah. But we need to like build a logical connection between them. So for example, if we have a solution to solve a particular problem, then why we need another solution, or why we, which also addresses the same problem or similar problems, right? So we need to know the the logical connection between things. So until now, we have talked about critical section problem, and we have seen how we can solve that critical section problem, right? Where we can achieve all three properties: mutual exclusion, no starvation, no deadlock, right? Now let's consider another situation where maybe we can start from that producer-consumer, or even more simpler problem. Let's say you have a process P1 and you have a process P2. And this process P1 has some statement S1, and this process has some statement S2, right? And what you want to achieve, or what you want to ensure, is that doesn't matter whether you are on a single core processor or multi-core processor, you always want to make sure that S1 is always executed before S2. Basically, what you are trying to do is you are trying to achieve the ordering between the execution of statement of two different processes, not the same process, two different processes. You want to make sure that there is no such situation where S2 gets executed before S1. S1 must be executed, and only then, after S1, the S2 can be executed. If S1 is not executed, S2 should not be able to execute. So basically, you are doing ordering or synchronization again between two processes. But can you achieve this using your current knowledge about synchronization? For example, using locks. So locks under the hood, they also use compare and swap and like atomic construction, like test and set. But can we achieve this using the lock?
Yes, but that'd be rather expensive.
Yes. Oh.
Because you're always constantly having to wait with the lock.
Can you draw on the board? Like we demonstrate on the board? Because maybe I'm wrong, but I think we cannot. But maybe.
Oh, okay.
Yeah.
Well, then you just.
But it doesn't mean, maybe as I said, maybe I'm wrong. So go ahead.
Okay. So to synchronize this, we could simply state that we have a lock over S1. And then we have another lock. And then once this is done, we can release it, which then goes on to S2. So wait, not that one. For S2. So once we release, and then release. So first we attempt to lock this one.
Mhm.
Then once it tries to execute,
Mhm.
if S2 is attempted to be executed, it can't go because this one is locked. Once that gets released, then this will finally can be locked, and then we can be released again. Kind of like the ensuring through locks, making sure that everything gets executed sequentially. I'm not entirely sure you do that in code, like it's like a rough idea. You can do it, but I'm assuming this would be very expensive because you're basically forcing everything to be serialized. So it's like a roundabout way of serializing data.
Thank you, thank you. Okay, so who think that his solution is correct? And anyone who thinks that the solution is not correct? Okay, anyone who thinks not correct? Oh, nice. So,
I think they're I'm gonna say it's probably correct because I'm assuming that I don't know.
okay. Remember, we have two different processes and we have multi-core environment. So they are like, if you have process P1 and you say walk, get the lock, let's say acquire the lock, and then do S1. And here you have process P2. So you are also saying here, first get the lock, right? You are trying to say the same thing, right?
Oh, wait, but you can't do locks at the same time because the process, or only one can have a lock at any given time.
Yeah, but let's say the locks under the hood, they do compare and swap or test and set. Let's say they use compare and swap and only one of them can execute. And let's say this one is lucky. It gets the lock. So it says get S2 fast.
Yeah.
But this is not what we want. We want to make sure that always S1 is executed. So when it releases the lock, only then this will get the lock and then it depends upon like
First come,
first, then let's say I don't know what the mechanism, but let's say randomly. Now after that, let's say it gets the lock and executes. So the order will be S2, S1. But we want to get S1, S2. Right? So what does it mean? It means that we cannot solve this problem using locks. Right? So locks can be used to ensure that only one process enters that critical section, but you cannot use them to enforce the ordering. You cannot use them to enforce the ordering, right? So, which means that we need some other solution to do that, right? Can you come up with a solution?
if I remember correctly from this one, we utilize the memory region. If I remember
Okay, thank you. Someone else. Try to think of some solution which you can use to enforce the ordering such that S1 is always executed before S2. And given that P1 and P2 are running on different cores. If I want S1 across, what is it? Go ahead.
So I was thinking that if OS can handle it because it's the boss, so it has to give the control to the S1 schedule, and then it can execute, and then we can move on to S2.
Yeah. So you are going in the right direction, but still, no, you need more details. So he's basically saying that if we give the control to the OS, and then OS allow P1 to execute first, and once it's done, then it allows the P2 to execute next. So then definitely there will be an order, right? But how does the OS knows that P1 has to execute first, and then P2 after that only the P2, inside which we have statement 2 can execute, right? So which means basically we need to somehow inform the OS that enforce this ordering, right? Go ahead.
As you were saying,
Sorry.
like you were saying, the memory barrier, right? If we enforce the memory barrier, can't that,
But memory barrier,
is that just within a process or?
memory barrier is only within a process. It is not across the process.
Is it possible to have like a check, so whenever S1 is done, then return that, like if it's done, to process two, that way.
Yeah. So combining what he said and you said, so combining that, we can build the solution. So you said that we need some mechanism to check that, okay, P1 is done. And once it is done, then it can inform the OS as he said, and then OS can do something to allow the P2 to continue, right? So basically what we do is this, like, we have P1, right? P1 does S1, and then it says, it tells the OS, I'm done. Okay, and then here we have P2, and it tells, OS tells, okay, go ahead, and then it does the S2, right? So this is what exactly we can do using the semaphore. So you give it a name which is named as semaphore. So for example, semaphore is a kernel level variable. I mean, you can define it in your user level code, but then it is maintained in the kernel level code. And it is like, you can request, S1 can request OS to manipulate the semaphore, but P1 cannot manipulate it on its own. It requests the OS to manipulate. So here what you do is, basically what you do is that you do the S1 statement, and then here you are saying OS, okay, do trigger, allow the P2 to execute, and then P2 can execute. So what, now this is like main philosophy and idea. Let me finish this and then we can take a break, okay? So what the semaphore does is like, you have there are like two types of semaphores, binary semaphores and counting. Let's first talk about the binary semaphores. Binary semaphores are like nothing, but they are variable, which can have only the value of 0 or 1. Okay, let's say it is an integer variable. It can have only value of 0 or 1. So initially, you initiate it to the 0. So let's say I have variable semaphore x, and I set it equal to 0. Now what the process 1 in our example will do is that it will execute S1, and then it will say increment x, right? And then it will inform OS. Actually, to increment x, it will ask the OS to increment. Okay, so OS will increment it. This on the other side, here this is P2. So here, what on the P2, what it is doing, it will check x. If the value of x is 1, basically if the value of x is 0 or less than 0, it will keep waiting. While x is less than or equal to 0, so keep waiting. And if it is not, then it will continue, it will execute S2. So here, what is happening now? It will say, it will execute S1. It will ask the OS to increment the semaphore, which was initially 0, and it set it equal to 1. So now what it will do is it will set that it was stuck here, P2. Now once x becomes 1, the loop breaks, the S2 is executed, and after executing, it will it can continue, right? But that is not the only thing. So how we increment, for incrementing, P1 will execute an operation on the semaphore, which is called as signal. So you don't ask explicitly to do increment, you basically say signal. So signal does the same thing. So signal is like an operating system call over the semaphore X. So within the body of the signal, this is what the kernel will do, not the application. The OS will do what? That it just simply increment the value of the X. So it will do X plus plus. But this is inside the kernel. As an application, you will only do signal X. Okay. On the other side, what you are doing is that you don't write while statement, you do wait. This is again a system call, and inside the kernel, what is happening is like while x is less than equal to 0, keep waiting, and if not, then decrement, and then do that. Okay, so every time when you do signal, the semaphore is incremented. Every time you do wait, the signal will not only test or wait on the while, but once you are successfully break the while, you decrement that. Okay, and
So-
after that, the control will come back to the application and will execute test. Yes, correct.
If we have several processes chained in this way, we still use only binary semaphore, or can we just keep increasing X?
Yeah, so this will take us, your question will take us to the other type of semaphore, which is counting semaphore. We'll cover it after.
So why can't we do the same process using threads? Like we
Using-
have,
Using thread.
yeah,
or
threads
using-
have like thread ID. So whenever X is equal to thread ID, then you go ahead and execute, otherwise wait, something like that.
Okay, I'm rephrasing your question and tell me if it is correct. He's saying, why can't we achieve the same ordering using thread IDs where where the OS says that the thread or the process, let's say, process A must execute before process B, right?
Yeah, but not the OS. Instead, in the thread itself, we can like add additional wait time. Like we have wait function, right?
Okay.
So whenever your thread ID is not equal to X, then wait some more time.
And you're assuming X is changed then.
Yeah, X is like some global variable which is changed by all the threads. So whenever X reaches that number, then
Okay. Okay, yeah, we can do that, but then we have a problem with that. Let's say you are an application developer, you are writing the code, you implemented your solution as you are saying, and it was fine. And next time you want to launch, first time you run your application with 4 threads. Next time you maybe want to launch, depending upon some condition, 10 threads. Which is what?
X got changed.
So every time you need to modify the X then, right? But here you don't. You have to just initialize signal. You need to define the type of the semaphore, binary or something, and depending on that, you take care. Right? I don't know whether everyone was able to understand his question or not. His question was like, we can achieve the same solution without using semaphore. Let's say we have 2 processes, and what we can say is that only that process can go ahead in its execution whose process ID is equal to X. And what we can do is that we can set first the process X equal to the process ID of P1. Once it is done, then we can change it X to P2, right? It will work, but then if I launch the same application, not with 2 threads, but 4 threads, the solution will not work because every time I need to change my code and the value of X, right? Any questions? The good thing is I like or I enjoy teaching in this way where we have more discussion, but it extremely is slowing me down. Like we are still on chapter 6. Okay, let's have a 10-minute break.
Sorry, we could do this. I was thinking, like, why can't we do this? Oh, participating in all these things.
Oh, okay.
Okay, and I'm thinking that I was initially thinking that after this we can cover the deadlock, which is chapter 8 of the book. But it looks like that we may not have sufficient time, and then I don't want to skip the topic of virtual memory, main memory, virtual memory. So I may shuffle the order where we first cover the main of memory, virtual memory discussion. And then if we still have time available, I can come back, to that talk discussion. Because at least now you are this is a undergrad course, so you at least have the idea, you know the terminology, or you know what is the problem of the deadlock, but you don't know the solution, but at least you know that what is the problem of deadlock. So you have like some initial starting points to investigate or to understand on the platform. But virtual memory is very critical, and I want to cover it first.
I mean, it's just, that's coming. Mostly, there you go. Oh, it's good.
Oh.
Very neat.
But I really
It's like
think
a-
that's what you
Very
I will back.
offer.
Oh, yeah,
I feel that. I could use. Yeah. It's like recycled. In my sense. I try to, recognize. I need sort of. But I see the vision. I see the vision. Yeah. What else is there? I feel like those have. So you usually like. Big challenges that you can with small people. I feel like you'll always find this like advanced and like, yeah, videos. Yeah. You get extra credit. That's like cost. Over the cost. I think
I do recall one.
you get my extra credit. Oh, wow. So.
Okay, so let's get back to our lecture. So we were talking about semaphore and someone asked the question that can we use the same solution when we have more than one process, right? I will come back to that question, but I just want you to realize the relationship between semaphores and locks. Okay. Okay. So when you have a binary semaphore, you can also use in place of locks or mutexes. Mutex is basically the same thing, right? Mutual exclusion. So you combine two words and makes a mutex. So because in mutex are nothing but what you are doing is you are preparing an library API or library functions that under the hood they are using the some atomic instructions like test and set to achieve the mutual exclusion. Right? So there are situations where you can use a binary semaphore to enforce the mutual exclusion just like locks. However, there is an additional thing which the locks cannot do but the semaphores can do, binary semaphores, which is ordering, right? So we can say that semaphores or binary semaphores are more general as compared to the locks in context of their properties, right? One thing. Second, so we have talked about this example where we have two processes and we wanted to enforce the order between them, and for that we use the binary semaphore. Now let's say we again have a binary semaphore and we have a different problem which we want to solve using a binary semaphore. So let's say we have, remember, producer consumer problem. We have a producer, we have a consumer, and they share a buffer. So let's say it has, I don't know, maybe 5 entries, right? So it can have at max the 5 elements at any given time in the buffer, and we know how it works. Producer produces the item, consumer uses it. Right? Consumer removes it from the queue and the buffer, and the producer puts the element in the queue. Right? But what is underlying assumption that there is always an order? Consumer cannot consume a item which is not there. If the queue is empty or the buffer is empty, consumer can't do anything, right? It must wait, right? So there must be an order, like producer must first produce and only then consumer can use it, right? So anyone who thinks that we can achieve this ordering using locks. No, why not? Why not?
Because you explained that blocks only shape which of the solution but not the ordering.
There is no ordering on the locks. Anyone can get the lock, depending upon which one of the requesters are allowed by the underlying hardware. There is no ordering, so we cannot use locks. Okay, can we use the binary semaphore to solve the problem? Who thinks we can solve the problem using the binary? Yeah, explain.
It's queue, right? So whenever we add the element, we have to first pop the first.
So let's talk in terms of weight and signal operation. Now you remember we talked about weight and signal operation, right? So how if we have a binary semaphore, then what should be the order of executing weight and signal from the perspective of producer and consumer to achieve this order? Anyone else?
Question, is the binary only for to synchronize two processes or?
No, you can use binary to synchronize multiple, but when we say binary, it basically means that it can take only two values, 0 and 1. So the value of the binary semaphore, it can never exceed than 1, and it is flat. Either 0 or 1, nothing else. Okay, let's say we have a binary semaphore. Let's say I have X, right? What I want to achieve, one, consumer cannot consume before producer produces an item, right? So basically, which means that producer must first produce an item and then signal the X. And initially the value of signal is the semaphore is equal to X. On the other side, the consumer must first wait and then consume the item, right? Now, let's say here on the producer side, I say produce an item and then put it in the queue or in the buffer, put in buffer, and then signal X, right? On the consumer side, what I say is wait on X, and then consume. Right? Whatever consume means, but it means basically retrieve the item, right? Do you think it is the right solution? What is wrong with this solution?
It doesn't tell the producer when to stop producing it, so the other has it, right? Like if you haven't, you might make more than the buffer can hold. If you only use signal.
Let's say we have an upper bound of the value of X. So here it is 1, right? So it is binary semaphore. So the value cannot go beyond 1. It will saturate there.
So then you can only make one at a time.
Is it a problem?
the buffer.
So is it a problem?
I mean, what's the point of the buffer then?
Yes, it is a problem because we are restricting the producer. Restricting the producer in the sense that we are saying you must produce one item, then wait for the consumer to consume it, and then you can produce the next one. So why we have the 5-element buffer if we want to do that? So we are not utilizing the buffer, right? So which basically means that the solution is it puts the order, it enforces the order, but only with respect to one element of the buffer, which effectively it assumes that the buffer size is 1, which is wrong, right? So how can we solve it? How can we solve it? If we allow our semaphore to take values more than 1, on the values more than 1, on the range of values. Now, what is the range of the values? From 0 up to the number of resources you have. What are the number of resources here? Resources each slot. So let's say you have 5 slots. So you have 5 resources, right? So what we do is that we allow, okay, our X semaphore can take on the value from 0 up to 4. Not 5, because 0, 1, 2, 3, 4. So now what it can do is that it produces an element, put it in buffer, signals X, so X becomes 1, right? It doesn't need to wait for the consumer. Let's say consumer is not executing. It is like, let's say it is not scheduled for execution, right? It doesn't need to wait now for the consumer. What it can do is that, okay, maybe come again, produce another item, put it in the queue, signal X again. So 1, 2, 3, 4, right? And when it comes to the maximum value, then it must sleep, right? On the other hand, let's say consumer, it was, let's say, sleeping, and then it is scheduled again for execution, and it finds, oh, the value of X is equal to 4. So what it does is that it executes wait on the X, which reduces the value of X back to 3. It consumes one item, then it comes back. It again says wait, which reduces the value again. So it becomes 2, it consumes, and so on. And when all the elements are consumed and the value of X is equal to 0, it gets locked, right? Which means it is put to the sleep, and it cannot execute. Basically, it keeps waiting. Remember, what was the internal implementation of wait? Wait was in the kernel. While X is less than or equal to 0. So in this case, we are assuming 1, right? So if less than or equal to 0, then keep waiting, otherwise decrement, and then consume. So actually here inside this, you are doing this one, and then you are consuming.
So in here, I can only start consuming at 5. I mean, in the value for.
You can start consuming anytime when value of X is not 0, greater than 0.
Okay.
But I was just giving you a situation where, let's say, the consumer was not scheduled for execution, and the producer was repeatedly producing until it fulfilled all the 5 items. And then, let's say in our example, the consumer was scheduled. And when it was scheduled, it gets the code, it sees, oh, the semaphore is 5. So it basically means that 5 elements are ready. So every time it keeps reducing, and when it reaches 0, it's. So, any questions? Okay. Let me just check if I am following the slides correctly. Synchronization, that tool that does not require busy waiting. This statement is not completely true. Why? I will explain. But for the time being, just skip it. Okay, don't focus it. This one. So semaphore S is an integer variable and a wait queue. This part and a wait queue, for the time being, ignore it. Okay, so semaphore S is an integer variable which is shared among processes, and it is a kernel variable. So kernel, you request kernel by either saying signal or wait to manipulate the value of the variable, right? So there are two standard operation, wait and signal. They are also known as P and V. Why P and V? Because the person, the computer scientist who first proposed this, he was I guess, Dutch person. So in the Dutch language, the words for wait and signal, they start with P and V. So he used P and V. So you don't need to worry about that. You can also call them as down and up, because signal, what does it wait? What does it do? It reduces the value, so it is down, and signal, it increases the value, so it is up, right? And semaphores can only be accessed via these two indivisible atomic instructions. Why indivisible? We will come back to it. But for the time being, semaphores can be accessed only, you can increment or decrement only by invoking the operations wait and signal on them, right? And these wait and signal, they are implemented as system calls by the kernel. Kernel must make sure that they are indivisible. Okay, why we are again talking about indivisibility? I will come back to it. Okay, so what is the meaning of this? Meaning of semantics of the operations? So wait. So wait is if s is positive, then return the reduce the value of s by 1 and return. Else, block or wait, right? So block or wait are two different things. Block mean that you are put into the process is put into the waiting queue, and wait mean no, it is not put into the waiting queue, it is still running, but it is just executing a while loop, but it is running. Okay. Signal, what is the semantic of signal? If there is a process waiting, wake it up and run. Again, just forget this one, I will come back to it. I don't want to like confuse the things, but for the time being, if signal, what does signal do? It will simply increment the s and return. This is what I have shown on the board. This part I will come back to it later. Okay. So wait body and signal body have to be executed atomically, because wait body and signal body, they both either increment or decrement the variable, right? And if you remember from the previous lectures, when you translate increment and decrement operations into assembly language, they translate into multiple instructions, and we want them to be executed in a atomic way, non-interruptible way. Otherwise, you cannot achieve the mutual exclusion, right? One process at a time. So hence the body of wait and signal are critical sections to be protected by the kernel. So binary semaphores, which we talked about, it is an integer variable that can range from only between 0 and 1. It is simpler to implement. It is also known as mutex. It is similar to as mutex locks. So you can use them to provide mutual exclusion, as well as you can use them to enforce ordering between the processes, right? Counting semaphores, they can take values from 0 to a upper value to a maximum value, can be used for other synchronization problems, for example, for resource allocation. Okay. Binary semaphores, they can be used to solve the critical section problem. And here is the example. Like, we have already talked about mutexes, right? They are locks. So wait on the mutex, and here your mutex is basically a binary semaphore. So when you say wait, so if you have initialized it equal to 0, let's say mutex is a semaphore variable, semaphore. So you initialized it equal to 0, a process which says wait will get blocked, or will be busy waiting, spinning in the while loop. Look at the board. So it will not be able to enter the critical section until another process signals it, right? And then it can do the remainder section. Or if the mutex is initialized to 1, then this process, only one process will be able to enter the critical section. Let's say if the mutex was 1, then wait will reduce it to 0, enter the critical section. So when I'm in the critical section, no one else can enter, because value of mutex semaphore is 0, so everyone else will be blocked. Then when I leave my critical section, I signal it, set it back equal to 1. Now anyone else which was like in the loop, in the wait loop, now can continue and enter the critical section. Okay. So you can use binary semaphore to achieve the same effect as mutexes or as locks. Okay. So this is the same examples. Two processes process 0, process 1 side by side having the same structure. Remainder section can be different. And this is the kernel. So wait and signal, they are the system calls. That's why they are indicated here inside the kernel, like they are implemented inside the kernel. And you can manipulate the semaphore mutates only by invoking wait and signal. If you have any question, you can stop me, okay? I'm going a little bit faster here because I have covered all this in discussion. The same problem example, which we had at the start of the discussion, you have process P0, P1, S1 is in P0, S2 is in P1, and we want to ensure S1 is always executed before S2. So how you can do this? By writing this code. Now you understand what is signal X and what is wait X, right? Okay, producer consumer problem. I have already talked about this. So let's say you have a buffer is an array of bus size cells, let's say 5 in our example. So producer, it can put an item into the buffer and just signal full cells, right? Then consumer, what it will do, it will first do the wait and then remove the item from the buffer and keep doing. And once it becomes 0, it will get stuck. And when it is full, it will also get stuck. Okay. Again, we are just showing that wait and signal, they are system level, system calls, and semaphore is maintained and manipulated only through the kernel. Okay, so here what we are going to see is that by using the semaphore, counting semaphore, our producer and consumer, they are synchronized. So here, let's say on the x-axis we have time, and on the y-axis we have the buffer size. And here basically what we are saying is that the number of the elements in the buffer, they start increasing, which basically what does it mean? That only producer is executing, not consumer. So the number of elements start increasing. And let's say after that, let's assume we have a single core. The producer is kicked out, consumer gets the chance to execute. So consumer executes, and as long as it executes, it reduces the number of the elements, right? In the buffer. Every time it says wait, right? After consuming every element. So and let's say before the semaphore becomes 0, the consumer is kicked out. Again, producer comes in, it starts increasing the number of the elements, right? Again, let's say after that, consumer comes in and it consumes all the elements. So once it consumes all the element, it gets blocked. So it is sleeping here. Consumer is sleeping here. And then let's say it is kicked out. Producer again produces some element, consumer comes in, consumes it. Then let's say producer gets the chance for a longer time to run, and it keeps producing the element to the point where your buffer becomes full, buffer size. Then at that time, your producer sleeps, right? So here what we are achieving, there is no situation where consumer can consume more than what the number of elements available. And there is no case where producer can produce more than the number of elements than the entries of the slots in the buffer, right?
The buffer is the shared memory.
Yes, yes. Okay, so one more thing. Here, what we are trying to emphasize is that the gap between the producer and the consumer is never greater than the buffer size, right? So here, so this red line, it shows you the number of the items consumed, right? And the blue line shows you the number of the items produced, right? Doesn't matter whether they are, let's say they are running on the different cores, not on the same core, producer and consumer, they are running on different cores, right? So let's say here initially, the consumer is not running. Our producer keeps running and it fills the buffer array. So you have maximum number of elements. After that, it sleeps, right? And let's say then consumer gets the chance. So it starts executing. So it starts consuming. When it starts consuming, the producer is also, a producer is also running at the same time. So it also starts producing. But the gap between them is never greater than the buffer size. Okay. So red is always less than the blue. because consumer cannot consume more than what producer has produced, right? So here is another example where we can use the counting semaphore. So let me read. I think it is very simple because we have already covered the problem of producer and consumer. So assume we have a resource that has 5 instances. Let's say you have 5 ALUs. You know ALU, right? Arithmetic logic unit. So assume we have a resource that has 5 instances, and a process that needs that type of resource will need to use 1 instance, right? We can allow at most 5 processes concurrently using these 5 resource instances. Another process, an extra process that want the resource need to be blocked. How can we code these processes? By using simply the semaphores. So one of the process will create and initialize a semaphore to 5 because we have 5 instances of the resource. So semaphore x is equal to 5. Then each process will have the same code structure. So it will first wait on x. So if the value of x is greater than 0, so what will happen that it will be reduced, and then after that we'll be able to continue. Use 1 instance of the resource and then signal x. Signal x, I'm done. So I'm releasing the resource. So increment the x, right? So we are ensuring that at any given time, at most only 5 processes are able to access the resource because there are 5 instances of the resource. Not more than, if 6 process comes in while 5 processes are, let's say all the 5 processes are here, they have not yet signaled. And if the value of the x will be 0, right? So if 6 process comes in and it says wait x, so it will get blocked. Right? Okay, so now let me go back to the now let me go back to the parts which I skipped. Synchronization tool that does not require busy waiting is not entirely true. I will come back to it. But let me first focus on this one. Integer variable and await. So what is the issue here? The units we have. Okay. You should not give me feedback next time. Okay. Okay. Okay.